Okay, so yeah, this week, as I said, we're going to talk, sorry, not this week, this meeting, we're going to talk about integration of functions on measure spaces. So last meeting, we introduced the idea of a measure space, um, and we saw how we could assign to certain collections of subsets the notion of a volume. And now we'll take this idea further, um, and we'll now talk about how can we use this notion of volume to measure or to integrate functions. But before we do that, we want to know what sort of functions are, good enough to be integrated. Because as we saw previously, there's certain theorems that we'd really like to hold, and so we want a theory of integration that allows us um, to have these theorems, but at the same time, we don't want we want numbers, or we want like the value of the integral to make sense. Okay. So we'll talk about this. Okay. So we'll first talk about integration of functions. So let x sigma mu be a measure space, and let f be from x into R. So there's a vast theory about um, functions from one measure space to another, um, and integration for like a wide variety of functions. But what we'll do for everything we need is we'll just talk about integration of real valued functions. And when I say real valued, I also do mean that infinite values are allowed. Um, so what I'll call this set R union minus infinity and infinity. I'll call it the extended real numbers. Okay, so it has an R with a bar over. Um, and we saw, I think last time, the how the Lebesgue measure extended to this extended real numbers. So okay, are we fine with the class of functions that we'll work with? We'll also see how this class of functions actually generalizes to integration of complex valued functions, like near the end. Are we okay with this so far? Okay, and we give the extended real numbers the Lebesgue measure with the Lebesgue sigma algebra. Um, Again, as I mentioned last time, it doesn't really, for any practical sense, in geometry, we don't really care about Lebesgue measurable sets that are not Borel measurable. Um, so in reality, you could also just choose Borel sets and you would have an equally decent theory, but we'll work in the Lebesgue sense since it doesn't actually change the theory too much. It's okay. Um, so um, we say F is mu measurable, um, is mu measurable if for every Lebesgue set, Lebesgue measurable set E and R, we have F inverse of E is in the sigma algebra. Yep. Um, okay. One more minor detail, that I forgot to actually mention last time. All the theory we will develop um, is for sigma finite measures. So what is a sigma finite measure? So So if again, if you have X sigma mu measure space, um, then mu is called sigma finite if there is a countable collection of measurable sets with finite measure that cover X. Okay. So this is one of the closest things we can get to a finite measure space. It's pretty much the next best thing from there. So some examples of sigma finite measure spaces is Rn with the with Lebesgue. So Rn with Lebesgue is sigma finite. Any probability space, so any probability space is sigma finite. And then you can probably come up with a bunch more. So yeah, we'll specifically work with sigma finite sets. So I won't really make the distinction of which theorem only works because of sigma finiteness. Um, but yeah, so that's about it. So okay, we've now defined the notion of a measurable function, and it's extremely similar to the definition of a continuous function, right? So I mean, it's basically the definition of continuous function, but we've replaced topologies with sigma, sorry, not sigma, with the Borel sets or whatever the sigma algebra is. Okay, so now one thing we should note, right, is so note um is that the Borel algebra, the Borel sigma algebra of R, um, and by extension the extended real numbers, can be constructed using sets of the form a to infinity. Okay. So what I mean by that is every Borel set can be written as the union. Um, Not quite. So how do I explain this? Okay. So the sigma algebra generated by sets of this form is exactly this Borel sigma algebra of R. So that's what I mean. Okay. So the sigma algebra generated generated by these sets is the same as the Borel sigma algebra. Okay. So that's what I mean. So in many situations, um, it suffices to check, um, in all situations actually, situations, it suffices to check that the preimage of this set is measurable. Yeah. So instead of checking like every sigma Borel set, what we can do is we can restrict to these open sets. Um, and in a lot of ways, these sets are actually much nicer because if you write out the definition, um, this tells you that you just have to check if sets of this form are measurable. Okay. Now, if you remember in Riemannian integration, the way we do it, so in the Riemann integral, we um so let's draw a picture. So in the Riemann integral, Say this is our function. The way we define the integral is we measure the volume of these rectangles, you know, we measure the volume of these rectangles. Oh, sorry. And then what we do is we make these partitions as small as we can, and we sort of take a limit, right? So we take a limit of the area underneath. But as we saw, this is not quite sufficient because sometimes what we can have is um, these approximations, right? Um, in very ill-behaved functions, such as the characteristic function of the rationals, we saw that the upper and lower sums never equal each other, let alone in a limit, right? So the way we'll rectify this is um, by looking at simple functions and approximating our measurable functions using simple functions. Okay, so the way we'll rectify this issue is instead of measuring down, what we'll do is we'll look at functions that take a finite number of values, and then we'll approximate this area instead. Okay, so we'll measure this area instead. And we'll see that um, even though right now it looks very insignificant, this is the major difference between Lebesgue and Riemann integration. So for this, we'll define, so we define now, so we now define um, a characteristic function. So a characteristic function of a set. So say again, we have x. So x will always be our measure space where we take functions from. Um, so then the characteristic function of E, so let E be a subset of x. Then the characteristic function of E is defined to be 1 if x is in E and 0 if x is not in E. Okay, so the characteristic function evaluated at x is 1 if we're in the set and 0 otherwise. One thing to notice about these functions is that xe is measurable, or sigma measurable, or rather mu measurable, if and only if E is measurable, right? Now, this is, I don't think it's entirely too hard to see why this is the case, because if you look at the pre-image of R, right, this must be E. And we know that R is measurable. So it's measurable if and only if the set itself is measurable. Um, so uh, hence measurable if and only if E is. Okay. Now we can also check that so if you have a topological space and you look at the Borel algebra of the topological space, one can show that every continuous function is also measurable. Yeah. So note every continuous function f from x into R. So here we've given it a topology. Is Borel measurable. If you remember, Borel just means the sigma algebra generated by the open sets. Um, okay. Uh, are we okay so far? Is everything okay? Okay. Now, um, wait, did I define what it means to be measurable in the extended reals or no? Does anyone remember? Okay, I'll just mention it quickly. So I'll mention it here. So a set E in the extended reals is measurable if and only if E intersect R is measurable. Yep. Um, sorry, I forgot to mention that. Okay, so um, yeah, let's now talk about some like one very important theorem regarding measurable functions, and that's um, the pointwise limit of a sequence of measurable functions is measurable. So, theorem. So if Fn is a sequence of mu measurable functions, then F equals the limit. Okay, let me write this slightly better. So f at x, which is the limit as n goes to infinity of Fn of x, is also measurable. Okay, so this is a very strong theorem, right? Because we saw again in the Lebesgue integral case where we had a sequence of functions um, that pointwise converge to the characteristic function of the rationals, but in some sense it wasn't Riemann measurable, right? So at least in the general case, we have that the sequence of functions is measurable, but again, we haven't really defined the integral, so we don't know if this is a useful notion yet. Okay. Um, but now I think we have enough theory to now define the integral. Okay. So the way we're going to do this is very simple. We're going to define something called a simple function. Okay. So definition, a function f from x into r is called simple if it takes on finitely many values. Okay. So what does that mean? So let's do an example of a simple function. Example. So the characteristic function is simple because it only takes on the values 0 and 1, right? It doesn't take on any other values. The function f of x equals x squared would not be simple. So f of x equal x squared is not simple because it takes in an infinite number of values, right? So we restrict to a very like nice case right now. One more thing to note is that every simple function um, can be written as a linear combination of characteristic functions. So let's just see that quickly. So every simple function is a finite linear combination of characteristic functions. And the way to see this is very if you can have f um, say f takes um, to see this suppose f takes on the values a1 up to an, right? Then define ei um, to be the preimage of the ith number. So this gives you some set. Um, and now you know that if it's on this set, it has to be one. So what you do is you just scale by that set, right? So then f is nothing but 1 to n ai c a ei. Okay. Does that make sense? So simple functions are basically just finite linear combinations of characteristic functions. And now we can see from this very clearly that um, a simple function is measurable if and only if each individual set ei is measurable, right? So these are very good for this reason. But simple functions are good for another reason, right? So suppose this is a big theorem that allows us to actually talk about integration. So suppose f from x to r is measurable. Okay, that's mu measurable. Then there is a sequence of sequence fn of um, mu measurable simple functions um, that are non-decreasing and bounded above by f. Um, okay, so what does this mean? So by non-decreasing, what I mean is that fn of x is less than or equal to fn plus 1 of x. So it's this at each point, the sequence is increasing. Um, and if, moreover, um, if f is bounded, then this sequence actually converges uniformly. Okay. Um, so yeah, this is very, very, very strong, right? Because you wouldn't expect any sequence of functions um, to converge uniformly. Moreover, measurable functions can be very, very bad, right? They don't have to be nice. Most measurable functions, in fact, are like disgusting to work with. So simple functions make life very easy because you can just work with a simple function and then we know uniform convergence is very, very strong, right? It's very, very powerful. So this is one of the biggest advantages of using simple functions to define integration. Okay. But now, if we look at a simple function, let's look at the graph of a simple function, right? Say it's something like this, then it bounces up and it's down here, and then it goes out till here, and then it's zero everywhere else, let's say, right? Now, it's pretty obvious of this function, um, that the integral of this function, so let's say this is a1, this is a2, this is a3, and this is a4, um, and then e1, e2, e3, e4, and this is our function f. So it's very obvious that the integral of this function, so the integral of this function over x with respect to the measure mu should simply be the areas here. right? Because that's how we define integrals even in the one-dimensional case, right? So it's very clear that this should be equal to the sum is n goes from I goes from 1 to n, ai times the measure of ei. Okay. So here f is equal to the sum ai cei, right? So it's a simple function. Does this definition of the integral make sense? Do you guys see why this should be the definition of the integral? Yeah, so it's quite literally just the area under the curve. Um, right? But the way we've defined it, the thing to notice very like the thing that's different is that um instead of looking at a function and then dividing it into like rectangles that could go to infinity, we've first considered functions that are just, rectangles that give us like a bunch of rectangles of different sizes. One thing to note is that we allow the integral to be infinite. Okay, so note, let me actually write this up here. Note, we allow the value to be infinite. Okay. We're not too afraid of infinities. Um, the definition of the integral is so necessary, in fact, that I think I'm gonna box this if I can figure out how to do that. Hmm, okay. That just put it. Okay, whatever. I'll just box it like this. Okay. But now we're gonna make use of the fact that we're gonna make use of the fact that we get given any measurable function, we get a sequence of measurable we get a sequence of non-decreasing simple functions that are bounded above by f, and we're going to define the integral to be the integral approximated by these. Okay. But there's one slight issue with just going there directly, right? Um, and that issue mainly is what if the function is negative at points, right? And what ends up happening now is if we naively allow to just approximate these functions, we could end up with situations where we have expressions of the form infinity minus infinity. These are highly undesirable. So what we're going to do is we're going to restrict to the case of positive or non-negative functions first. Okay. Non-negative measurable functions to begin with. Okay. So let's start there. So suppose, oh yeah, so we don't generalize directly since um, if f is allowed to be both positive and negative, we might end, oh my God, end up with situations where we have an expression infinity minus infinity. Okay. So to avoid this, what we're going to do is, so we now let f from x to r measurable and non-negative. Um, then what we're going to do is then define. So we're going to define the integral over x of f with respect to the measure mu as the supremum, okay, of the integral um, of some function s d mu. But okay, what functions do we know how to integrate? We know only how to integrate simple functions, right? So we're going to take non-negative simple functions that are bounded above by s. Okay, so s is simple and measurable. So this is how the integral is defined. Okay. Are there any questions as to why we've restricted to like non-negative functions to begin with? Because it is like non-trivial, right? Like you would expect that similar to the case of Riemannian integration, you can integrate whatever function you want. I mean, up to some restrictions. Um, but having a restriction on the value of the integral seems, sorry, value of the function seems quite weird. So if there's um, any questions, please ask now. Are we good? Can I explain a bit more about why? Okay, yeah. Okay. Um, so okay, we've been making use of the fact that um if f is measurable, then we have a sequence of so if f is measurable and we have then we get a sequence of simple measurable functions that approximate f, right? Um, and then the way we've defined the integral is then um, as a supremum over um, all possible values of the approximated integral. Um, so the issue then becomes that if you allow negative values as well, and mu, like one of your measurable sets has infinite volume. So, I mean, we can give a very simple example, right? So if you look at the function defined as positive up here and the negative down here, right, in all directions, um, this function is certainly measurable, right? Um, but then what happens is that the integral, let's call this like f. So what happens is that the integral over r of f by definition would be, let's say this is 2 and let's say this is -1. This would be 2 times the uh, volume of this set plus -1 times the volume of um, this set. But both of these have infinite volume. So what you end up with is 2 times infinity minus infinity. Okay. So you run into issues like this, where if you if you simply allow any values of AI here, you you run into trouble such as infinity minus infinity. And then it's how do you how do you resolve what infinity minus infinity is? So even in the definition of simple functions, we do require that, like we require that we have like positive, um, yeah, we have like non-negative simple functions. Does does that give you like the answer you were looking for? Or like, does that make sense? Like, is that
Yeah, that's good.
okay? Um, so yeah, I mean, here again, there's an asterisk here saying that make sure you don't run into infinity minus infinity. Thank you for pointing that out. Um, because Yeah, so we do restrict ourselves to non-negative. So let me actually just make the let me actually just make this more clear. So here restrict, here define, sorry, here define the integral for non-negative simple functions. Okay. We'll get to like how to deal with this like how to deal with like negative things in a second. Okay. Okay. So now, but again, this seems a little upsetting because there are many functions that we would like to integrate that are both positive and negative. So how do we deal with those functions? So how to deal with functions that are both positive and negative. And the answer to this is very simple. So say we have some function f, right? What we're going to do is we're going to extract the positive part and we're going to extract the negative part. Okay. So we extract the positive and negative parts. Okay. So the positive part of f is just simply um, is simply equal to f. Let me write this slightly nicer. So we have the positive part of f of x is f of x if x is bigger than, sorry, if f of x is bigger than 0 and it's 0 else. Okay. And then we're going to define the negative part, f negative of x is going to be minus f of x if f of x is less than 0 and 0 else. Okay. So in the function above, so in the case up here, what you get is that the function, so you get f of x is 2 if x is bigger than 0 and minus 1 if x is less than or equal to 0. So the positive part of f is simply 2 when x is bigger than 0 and 0 when x is less than or equal to 0. And the negative part of f is 1 when x is less than or equal to 0 and 0 else. Okay. So now we see that the positive part plus the negative part of f is not equal to f. Okay. So I guess like calling it the positive and negative part is slightly weird, but um, yeah, what you end up is with f is equal to f plus minus f minus. Okay. Um, yeah. Is this clear? And one thing to notice is the absolute value of f is f plus plus f minus. Okay. Now f plus and f minus are both measurable and non-negative, which means that we know how to integrate them. Okay, so we can look at the integral of f plus and the integral of f minus. Now what we do is we look at if they're both finite, right, we can simply just subtract the two integrals and get the integral we want. Um, but the more general case is, but if one is like non-infinite, so if one of them is finite, we can define the integral of f to simply be the integral of f plus minus the integral of f minus because of this thing. Okay. Is this clear? Oh, does this make sense? Okay. So, so yeah, I mean the Lebesgue integral and the Riemann integral look extremely similar in their definitions, right? In both cases, you're sort of approximating your function, but in the Riemann case, you're approximating the set, right? In a sense. And the partitions that you're allowed to make, excuse me, the partitions you're allowed to make are quite limited. Okay. Um, you're not allowed to make very ugly looking partitions. That's sort of what the Lebesgue integral fixes, right? Um, it sort of lets you make partitions that are more ugly, but still like manageable. Um, but and then you approximate your function by um, a sequence of non-decreasing simple functions. Basically, you're taking a lower sum, right? Yeah, you're taking a lower sum, but with more like ugly looking functions. Um, another thing, another piece of notation, sorry, another definition is that we note that the integral of the absolute value of f is equal to the integral like this. And we note that if f is measurable, then the absolute value of f is always measurable. Um, moreover, it's always integrable, and you get a sensible value for the integral. We say f is Lebesgue integrable if and only if the integral of the absolute value of f is finite. Okay. So this is what it means for f to be Lebesgue integrable. Now, one thing to note is because we've defined the integral in terms of supremums of simple functions, we can see that if we scale your function, like if I scale my function, um, I simply just scale every simple function I use to approximate f, and I get an integral that's the scaled version of my original integral. So this means that like I can pull out scalars outside my integral. Another thing is supremums behave well with addition. Um, and moreover, the sum of the integral of two simple functions is the um, sum of the integrals is the integrals of the sum. So what this tells you is that the integral is linear. I mean, which is what we would expect, right? Because the Riemann integral was linear. So if we created an integral that wasn't linear, that would not be nice for a lot of the applications that we have. So okay, is the definition of the Lebesgue integral. So this is called the Lebesgue integral. Um, yeah. So is the definition of the Lebesgue integral clear? Okay. Now let's talk about the most important spaces. Um, that we study in functional analysis and in physics. Um, so in physics, whenever we look at wave functions, for example, we require that our wave function be normalizable, right? So what does that mean, right? So in physics, actually, before I go there, let me define. So so let f be a function from x into c, because in physics, again, we a lot of the times we have complex valued scalar functions. Then f of x is equal to u of x plus I times v of x, right? Um, if f is measurable, so the way you do it, you give this thing, you treat c as R2 um, with the Lebesgue measure. So you can ask whether f is measurable or not. And then it turns out that if f is measurable, then u and v also have to be measurable, right? So if f is measurable, u and v are also measurable. And so we define the integral of f as the integral of u plus I times the integral of v. Okay. Very, very simple. I mean, it's a very straightforward generalization. Okay. Now, with this out of the way, we in physics, we talk about when we're doing quantum mechanics, we talk about um, state space and solutions to the Schrodinger equation. But one of the postulates of quantum mechanics say that the probability must be one. And then the way the probability is defined, so is is that the integral over all space of these um, wave function squared is finite, right? Because if it's infinite, it's not normalizable. So it might still solve the Schrodinger equation, as in the free particle. Yeah, in quantum mechanics, the free particle is not normalizable. So what that tells you is that we have a um, that it's not a physically realizable state. Okay, so we require that the square of the absolute value of the integral is finite. Um, and so this actually generalizes to a large variety of a large class of functions. So we define the so-called LP spaces. Okay, so we now define the LP spaces, and the way they're defined. Let me here. P is any number bigger than or equal to 1. There's also a definition for when P is infinity, um, but we will probably not need it. So I just won't define it because it requires a lot more definitions. So okay, so the LP spaces are defined to be functions into the extended reals. Again, you can replace the extended reals with the extended complex numbers if needed, and like all the definitions um, transfer easily. And what you require is that the integral of the absolute value of f raised to the power p is finite. Okay. Are there any questions regarding the definition of the LP spaces? Okay. Now, the thing is, we can ask ourselves, is this a vector space? We can also ask ourselves, is this normed? Um, it has a very simple norm, right? It has a very simple norm. What you do is you define this to be the pth root of this integral. Um, and then you can use like Holder's and Minkowski inequalities to show that this is actually a norm. But you see, there's actually a very big issue with the way we've defined this space, right? And that issue is that when when we look at functions that differ on a set of measure zero, you get that the integrals are the same. And so what this sort of tells you is that there are many, many, many functions um, that act as the zero vector in the sense that the norm remains the same when you add by them. And now this is clearly an issue, right? Because if I'm adding a non-zero function, I shouldn't be able to just stay where I am. So what we do is we define an equivalence relation. Yeah. So to rectify this, we define an equivalence relation um, on LP by so what do we do? We say f is equivalent to g if and only if the integral of um like if this integral is zero. Okay. Um, very simple. I mean, basically, if two things have the same integral, if they have the same norm, we just say that they're equal. Let me actually just make sure that this is how you do it because this looks wrong. Um, this looks a bit too restrictive, actually. Just hold on, give me a second. Because it's either that their norms are the same. No, that can't be right. The reason for that is because then everything on the same ball would have zero integral. So it would have the same integral, which is clearly wrong. So because like you wouldn't have like balls, you just have a straight line of functions. Um, okay, no, apparently it is this. Okay. Okay, no, I don't like this too much. So what I'm gonna say is that um Okay, so the way we're actually gonna do this is we're gonna define a new thing. So we have like a small side here. So say you have say we have some property, okay? Some property A. And what I mean by this is like let's say the property is F equals G, or F doesn't equal G, or is the cat black, or something like that, right? If we have some property A and the set X in X such that X satisfies A is of measure zero, then A is satisfied. Uh, X doesn't satisfy, sorry. Then A is satisfied almost everywhere. Okay. So if two things, um, so if you have the property saying F equals G, right? Then we can say, okay, if F and G differ on a set of measure zero, then F and G are equal almost everywhere. Okay. So so what we're gonna do is we're gonna say that F is equivalent to G if and only if F is equal to G, AI, sorry, AE, where this is F and G are the same everywhere except a set of measure zero. Okay. So let's do an example just to make sure we understand this. So say we had f of x equals x squared, and then g of x equal to 0 when x is equal to 1, and then x squared else. Then the set of points where f and g are not the same, right, is just equal to the singleton 1, but this is measure 0. Does that make sense? Like, does equality almost everywhere make sense? Okay. Now what we're going to do is we're just going to, so we've defined this equivalence relation where two things are equal almost everywhere. Um, so then we define the main space LP of X, right, to simply be the equivalence classes that we get. Okay. Now, this is a very, very important space because again, um, when we're talking about quantum mechanics, we look at L2 spaces. When we're doing Fourier analysis, we look at L2 spaces. When we solve PDEs, um, we talk about a slightly weaker class of functions, but they're still um, all subsets of LP, um, I think. And these are very, very, very well behaved when it comes to our like infinite dimensional spaces, right? Um, they're well behaved in the sense that firstly, they're Banach spaces. Okay, these are Banach spaces. So we already know that we can do so many things on Banach spaces. So for one, they're complete. So Fourier analysis becomes very nice. Um, we can approximate solutions to Schrodinger's equations for L2, for example. And in the sense that the approximations are very precise, and we can get them as precise as we want, right? Using L2 functions. Um, and these are also nice in the sense that they're there's isometrically isomorphic to their dual spaces. So what does that mean? So firstly, if you look at LP, um, right, you can now define a function. So we can define the function, um, and I'll call it EV of f. And what that does is it takes a function L in LQ, and then gives you a real number. Maybe next, I'll give you a real number. Defined, oh, defined by EVF of G as the integral um, of FG d mu. Here, F is in LP, LP, oh my God, LP, with 1 over P plus 1 over Q equals 1. Um, this equality now might seem extremely random, but um, you need it for something called Minkowski's inequality. So um, it turns out that it is an important, um, it's an important, sorry, it's an important condition. And then what you find is that if F is in LP and G is in LQ, then F times G is in L1. Um, it's slightly non-trivial to prove that actually, but it can be done using Minkowski inequality. Um, and now what you see is that this EV of F, like EV at F, is in the dual space, um, right? Is in the dual space of LQ. Moreover, um, there's some like strong theorems in analysis. I think they're called the Radon-Nixon theorem. Um, you can use the Radon-Nixon theorem to show that this is actually an isomorphism. What's the Minkowski inequality? Let me look that up because I don't actually remember. Um, okay, so the okay, so what it says is that was I actually supposed to use Holder's inequality? Oh yeah, sorry, this is actually for Holder's inequality. And what that inequality says is that the L1 norm um, of FG1 is bounded above by the P norm of F and the G norm of Q, where 1 over P plus 1 over Q is 1. Um, so that's Holder's inequality. But to prove Holder's inequality, you need Minkowski's inequality. Or one of the ways. It's something like that. You either need Holder's inequality or Minkowski's inequality to prove the other. Um, but yeah, Holder's inequality just says that the product of um, an LP and an LQ function is L1 when you have 1 over P plus 1 over Q is 1. Okay, so I mentioned that this isomorphism was isometric, um, and is isometric. And what I mean by isometric here is that the isomorphism is distance preserving. Okay, so let me just I'll say that is distance preserving. Okay, because we have a norm on LP. That's how we made it a Banach space. Um, and then Banach space, the like dual spaces of Banach spaces, um, the continuous dual, I should mention, like make sure this is the continuous dual. The continuous dual of Banach spaces must like they inherit the supremum norm, which then makes them a Banach space. So we from that norm we can then talk about distance. Um, and this isomorphism just preserves distances. And so in a lot of contexts, what we can do is we can then say that LP of like the LP space is the sorry, the dual of the LP space is nothing but LQ. Okay. But you might have noticed something, right? You might have noticed the fact that if P equals 2, then Q must also be 2, right? So what this says is that LP, note, that L2 is isometrically isometrically isomorphic to its own dual space, right? Now, this has some profound implications that we might explore um, when we talk about quantum mechanics later on. But for now, I mean, we know that finite dimensional vector spaces are isometrically isomorphic to their dual spaces. So L2 in some sense can be thought of as a finite dimensional vector space, right? Even though this very, very big um, infinite dimensional vector space can be treated as a finite dimensional vector space. Okay. And that comes in handy a lot because, for example, now we know that this is a Hilbert space. Like we know L2 is a Hilbert space. Um, and since it's a Hilbert space, we can talk about orthonormal basis. Um, and we can reduce an um, uncountably infinite basis to a countable infinite one, which is used a lot when we talk about Fourier analysis. Is it a coincidence that the one norm has the same notation as the trace norm? Um, this one? Um, I mean, this is just the standard notation for norms. Um, and like when the norm is known, you can sort of just, you know, um, you can be very like you don't have to be too stringent when it comes to um like your notation. You can be very loose with it. But yeah, these are just the standard like notations for norms. Um, okay, so I mean, I'll rewrite this as LP. Okay, because that's what I used below. Okay, are there any questions about LP spaces so far? So we've concluded our discussion about LP spaces for now. We've I'm pretty sure to show that um, to use the Radon-Nixon theorem, you need that X is sigma finite. So that's one place we've used sigma finiteness. Um, but yeah, we'll make use of the L2 spaces quite a bit um, when we talk about like PDEs on manifolds, if we talk about PDEs. Um, okay, so that's some like function spaces. Now let's talk about why the Lebesgue integral is uh, better, in my opinion, than the Riemann integral. And those are these two following theorems. So the two big. So the first theorem is the monotone convergence theorem. So the monotone convergence theorem says the following. So suppose we had a sequence of functions. Moreover, these functions have to be non-negative. Yeah. And measurable, but since we're talking about integrals, I'll leave that out. Um, and Fn is less than or equal to Fn plus 1. Then the limit as n goes to infinity of the integral of Fn is equal to the integral of the limit. Um, this is the most important theorem. Um, well, with the dominated convergence theorem that we use with integration all the time, right? Um, because because of the way we've defined the integral, when you when you go to like countable spaces, right? If x was countable, um, and non-continuous in a certain sense. So, like for example, q would be almost continuous. So when I'm talking about things like the integers or the natural numbers, the integral is actually then just a sum, right? So what this is saying is we can swap limits and sums very nicely. Okay. So the monotone convergence theorem is very, very, very powerful. And we use it all the time when we're doing approximations with Fourier series. I keep bringing up Fourier series because a lot of this theory was developed because of the inadequacies of the Riemann integral to deal with Fourier analysis. Okay, and Fourier analysis is by far the most important application of math that's come out for things like signal processing and approximations of PDEs and the Schrodinger equation and whatnot, right? Um, so being able to deal with the Fourier, being able to deal with Fourier series nicely, um, gives you basically infinite power when we're dealing with these things. And the second thing is the dominated convergence theorem. So the dominated convergence theorem. The dominated convergence theorem is suppose Fn is a sequence of measurable functions. Um, you don't need them to be non-negative this time. Functions um, with the limit. So if I call the limit f, um, then if there is some g in L1, um, such that fk is less than or equal to g for all k, then f is Lebesgue integrable. Okay. Not only is f Lebesgue integrable, um, we know that f, like we know the integral of f. The integral of f is precisely um, the limit of the integrals. Okay. So the dominated and monotone convergence theorems are immensely powerful because we can simply just swap limits and integrals in a much, much, much less restricted setting, right? We no longer require that the sequence of functions uniformly converges, for example, right? Because uniform convergence on its own is an extremely terse requirement. We saw how like the we saw how a Fourier series, like last week, I think we saw how the sequence of cosines, right? They're bounded, they're all L1, right? Um, but the function they converge to is um, non-integrable. Okay. So we've already seen an example of where the Lebesgue integral was strictly required to talk about Fourier analysis and the Fourier series of certain functions. I just want to leave off with like one example integral. So let's compute the integral over 0, 1, okay, of the characteristic function of the rationals. Okay. If we remember, this was extremely hard. I mean, this is not even Riemann integrable, right? Um, but it is very easily Lebesgue integrable. And we see that it's just the measure, because it's a simple function. So it's 1 times the measure of q in the rationals. And if you remember last time, we showed that the measure of a countable set in the Lebesgue measure is 0. Okay. So we have that the characteristic function of the rationals is 0. Moreover, we also saw that um, um, sorry, we saw that the characteristic function is not Riemann integrable, but it is Lebesgue integrable, and the value is 0. Okay. So this is a better way of defining the integral. The only downside with this definition is that we don't have a notion of orientation. Okay. So downside, no notion of orientation. Okay. So to fix this, right? Um, to fix this, we define the integral over AB of f as the integral from a to b, and we write it like this. Um, I'll write f of x. And this is by definition, like we define it to be the negative of the integral from b to a of f of x. Okay. So this encapsulates orientation. Okay. Are there any questions? Are there any questions regarding this? Okay. So in that case, I'll end the meeting here for now. And I'll see you all next meeting.